All right, today we're pulling back the curtain on the simple but incredibly powerful engine that basically kicked off the entire modern AI revolution. We're talking about the deep feedforward network. Let's get right into it. You know, it's a question that feels like it should have some ridiculously complicated answer, right? But what if I told you that so much of the powerful AI we see today, from Wall Street to hospitals, is all built on a foundational idea that's, well, surprisingly straightforward? Let's go find that blueprint. Okay, so at its core, a deep feed-forward network, or a DFN, is just a one-way street for data. Information comes in one end, it flows through a bunch of processing layers, and then a prediction pops out the other side. That's it. No loops, no going backward. Now, the deep part, that's the real key. It just means you have multiple layers stacked up, and it's in that depth where all the magic starts to happen. To really wrap your head around it, just picture a DFN as this super smart assembly line. You feed it raw materials, and out comes a finished product. So let's take a little tour and look at each station on that line. So every network really has three main sections. First up, you've got the input layer. Think of it like the loading dock. All it does is accept the raw data. Could be the pixels from a picture, numbers from a spreadsheet, whatever. Then that data moves into the hidden layers. Now this is the heart of the assembly line. This is where all the heavy lifting, all the pattern spotting actually gets done. And finally, everything arrives at the output layer, which makes the final decision. You know, is it a cat or a dog? Is the stock going up or down? So what's actually going on inside those hidden layers? Well, they're packed with things we call neurons, and each one is basically a tiny little decision maker. It looks at all the signals coming in from the previous layer, it weighs each one based on how important it's learned it is, and then it asks a simple question. Is this combined signal strong enough for me to get excited and pass it on to the next guy? It's just a massive cascading chain of these tiny little judgments. And here's where it gets kind of mind-blowing. There's this thing called the universal approximation theorem. And what it proves, basically, is that even a simple network with just one hidden layer can, in theory, learn to mimic almost any continuous pattern you can imagine. Think of any smooth, unbroken line on a graph. It can learn to draw it. That is an insane amount of potential packed into such a simple structure. So the potential is there, but how does it learn which patterns it's supposed to look for? It doesn't start out smart. In fact, it starts out incredibly dumb. It learns just like we do, by making a ton of mistakes and getting corrected, over and over and over again. And that learning process is this really elegant four-step loop. First, you have the forward pass, where the network takes its best shot and makes a guess. Second, we calculate the loss, which is really just a fancy way of giving it a score for how wrong it was. Third, and this is the absolute secret sauce, is backpropagation. That error score gets sent backward through the network, telling every single neuron how much it contributed to the mistake. And finally, gradient descent acts like a mechanic, using that feedback to just slightly tweak all the internal knobs and dials to get a little bit better next time. You repeat that loop millions of times, and you go from mistake to mastery. So yeah, that loss function is absolutely crucial. You can think of it like a really tough teacher who's grading the network's homework. The entire goal of training is just to make that score, that grade, as low as humanly possible. A low score means you're getting it right. And this is why backpropagation was such a game changer. It's not just about telling the network, hey, you were wrong. It's about assigning very specific blame to every single connection inside. It's like a great coach who doesn't just yell at the whole team after a bad play, but instead goes to every single player and gives them precise individual feedback on what they need to do better next time. It's incredibly efficient. Okay, so we get it. This system is powerful, but what actually gives it that power, and what are the trade-offs? Let's dig into the key ingredients and, well, some of the headaches that come along with them. This right here is why deep matters so much. A shallow network, maybe with just one hidden layer, it might learn to spot simple stuff, like basic edges or colors in a picture. But a deep network, it can take those simple patterns from the early layers and use them as building blocks for more complex ideas in the later layers. So layer 1 sees lines, layer 2 says, hey, those lines look like an eye. And layer 3 says, okay, 2 eyes plus a nose, that's a face. It's building a hierarchy of understanding. The other secret ingredient is something called an activation function, and its one crucial job is to add nonlinearity. Now, here's what that means in plain English. Without it, no matter how many layers you stacked up, the network could only ever learn simple straight-line relationships. The activation function is what lets the network learn the messy, complex, curvy patterns of the real world. It gives it flexibility. But going deep comes with its own set of problems. As that error signal travels backward through all those layers, one of two bad things can happen. It can either fade away to basically a whisper, that's the vanishing gradient, or it can snowball into a massive, useless number, like a deafening scream. That's the exploding gradient. And in both cases, learning just grinds to a halt. It's a huge challenge. And of course, there are a couple of other classic hurdles. There's overfitting, which is basically when the network becomes a bad student who just memorizes the answers to the test instead of actually learning the concepts. And obviously, training these things takes an enormous amount of computer power, which is why we rely so heavily on specialized hardware like GPUs. But despite all those challenges, the impact of the deep feed-forward network is, well, it's impossible to overstate. It is truly the foundation of the AI that we see all around us every single day. I mean, seriously, the principles we just talked about are at work everywhere. They're helping forecast the stock market. They're spotting diseases in medical scans. They're powering the basics of how your phone translates languages. And they are the absolute bedrock of modern image recognition. So while they might not be grabbing the headlines like the latest giant AI models, you have to understand that DFNs are the bedrock. They are the first principle that everything else in deep learning grew out of. If you understand this simple blueprint, you understand the origin story of modern AI. And that kind of leaves us with this huge, fascinating question. If this relatively simple one-way flow of information was enough to spark this entire deep learning revolution, what fundamentally new blueprint is just waiting out there to be discovered? What's going to power the next generation of AI? What comes next?